In any case, so we're going to talk about general relativity today. My goal here, and it's ambitious, is to make this a layman understandable talk. Unfortunately, the math that goes into GR is pretty involved, which is why it typically doesn't get covered until a first or second year graduate course. Typically it's never even touched in undergraduate physics degrees. It's
I'll try to
pretty
fix
involved
that
stuff.
starting in the second half.
Sounds good. It has, I think, kind of a unique place in popular culture and the popular imagination. I think it's for a couple reasons. One is that it deals with a lot of celestial objects that are kind of cool and exotic, like black holes and neutron stars and that kind of thing. Which just, it's just easy fodder to make a sci-fi movie about. Also, the way that the theory operates, the way it describes space and time, is so completely different from anything that we're familiar with in an everyday sense, that it really just kind of takes people back into, and I think that also makes it really interesting for a lot of people. And it's unfortunate that it's not as accessible, just given how damn complicated it is. So I'm going to do my best. When I first worked on this talk, I tried to put in some derivations of some of the central quantities that are involved to try to prove maybe where some of this stuff comes from. As I was working on it, I realized that was just too ambitious for this level of the talk. So what we're going to do is I'm going to give a brief introduction to the subject, and then spend a fair amount of time, maybe 15-20 minutes, just talking about curvature, because it's so important in GR. And then we're going to go through a number of very important results from GR. General relativity is called GR for short. We'll go through a number of important results, and I'm not going to prove them, I'm not going to derive them, but I'm just going to put some equations on the board with some pictures and try to just kind of explain what the equation means, what it does, how it operates, just to give at least you guys a broad, intuitive picture about what the theory is saying. And so then this type of lecture admittedly has some shortcomings, so you're going to probably be left with a lot of questions, and I'm not going to be able to answer them because it would take probably a couple semesters of graduate level instruction to really get to the bottom of some of this stuff. But hopefully, you guys will be left with a little bit of something that you didn't understand before. So we will see how it goes. So to begin, before we talk about GR, we need to talk about its precursor, which is, of course, Newtonian gravity. This is our good friend Isaac, who lived back in the 1600s. And he worked out this model of gravity that involves his main two equations for it. Of course, we have, if anyone took a first year class of physics, you would have gone over this. The force of gravity between two objects is equal to minus the gravitational constant, which is a very small constant. Gravity is a very weak force, which is why you have to have very large objects like the Earth before you have an appreciable amount of gravity. Even though I may be emotionally attracted to somebody, I'm not physically attracted to them with gravity unless I was very, very large. So G is very small. It's around, I think, 10 to the minus 12 in, I believe, in SI units. So we have minus this constant G times the product of the two masses involved, and divided by the square of the distance between them, so the force drops off as r squared. And then the direction of the force is minus this r hat vector, which is the direction separating the two masses. So it just says that two things are attracted, the minus sign means attraction, and the magnitude of the force has this behavior. So that combined with his second law, which shows that the force equals mass times an object's acceleration, that is enough to derive a whole bunch of very interesting properties. The main paradigm shift that Newton introduced was he was able to unite both the motion of the celestial bodies and the motion of the proverbial apple falling out of the tree. He was able to unite those under this single common law of motion, which was really a real paradigm shifting type of discovery at the time. And also there's some cool results that come out. So if you look at, he was able to work with both these equations and his calculus. He was able to derive the elliptical motion of planets around the sun. And he was able to show this interesting result that if you take the area of an arc subtended by a planet over a certain period of time, that area is constant over any period of time during the object's orbit. So meaning when the planet is out here, it's moving very slowly because it's farther away, doesn't have as much force of attraction, but it's farther away, so you have this area which is, has a larger contribution from the length. When it's close in, it's moving a lot faster, but these two areas are actually identical, assuming that they were subtended in the same amount of time. So pretty cool stuff. But as it turns out, it is not exactly correct as a theory, in particular when you have very large masses, when you have very large distances, and when you have very fast speeds involved. This description of how gravity behaves breaks down. And I found this quote of Sir Newton, which I thought was pretty neat. He's kind of seemed to anticipate this in a sense. He says, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. Nice quote. Which brings us to our old buddy Einstein. I love this picture. Here it's great. So Einstein came up with, I don't know how he came up with this. Well, you can sort of follow it, I guess. But he had this brilliant idea to completely redescribe how gravity operates. Instead of describing it as a force between objects that are pulling on each other, he described it instead as a deformation of space and time in such a way that what appears to be an object being pushed is actually an object doing the closest thing it can to being essentially unaffected in the curved space-time. So he described gravity as a geometric deformation of space and time in such a way that leads to what looks from the outside as being orbiting bodies and forces and that type of thing. And that's the central thing I'm going to try to explain, is what exactly that means. There's a lot packed into this statement. What does it mean to geometrically deform space-time? And that's a good question. We're going to try to get to that through a roundabout way in the next 45 minutes. So the first thing I want to talk about is his equivalence principle. Einstein famously said this was his happiest thought when he realized this equivalence. And the idea proceeds as follows. So here on the left we have Newton in a box. He can't see out of the box, and the box is just sitting on the surface of the Earth. He takes an apple out in front of him and he drops it. And of course you'll see the apple accelerate towards the floor and hit the floor at some rate. That's situation A. Situation B, you have Einstein in an identical box that's out in outer space. It's very far away from any planets, doesn't experience any gravitational pull. However, the box is accelerating upwards at 9.81 meters per second, the same as the acceleration of gravity. And he also holds an apple out in front of him and drops it, and it'll appear to accelerate down towards the floor. Of course, from outside the box, you can say, oh, situations are different because this one is accelerating and the box is moving, this one's stationary. Einstein's epiphany was that, so first of all, from within the box, there's no way for Newton or Einstein to tell which of the two situations they're in, at least with one small caveat that I'll get to about tidal forces. But it'll appear to be the same, and then he further postulated that there is no way to physically distinguish the two situations if you're not able to look outside the box and see if you're in a gravitational field or not. And it turns out that that is correct. His epiphany has been validated very well experimentally, and it turns out that these two situations are actually equivalent. And that's kind of the main conceptual stumbling block that I'm going to try to explain, is how does that make any sense? How can a person not moving that's just in gravity, how can that be the same as someone that is out in outer space and is accelerating? And there's, if you think about the converse situation, so think about how they film movies in outer space, right? So Apollo 13 or whatever other space movies, they get these airplanes that fly up really high into the atmosphere, and they send them into free fall where they enter this. They get up really high, then they turn off the jets and just freely fall for say 15 minutes before they turn the jets back on so they don't crash. And during this 15 minutes when they're freely falling, then all the actors in the airplane will of course float up, and it looks like they're weightless, and they're able to film space movies that way. So for them, it appears very much like they're weightless. And then for this case, you feel very much the same, right? So if you're accelerating, you feel the ground pushing you up, and then if you're just standing here or sitting in your seats, you also feel the ground pushing you up in the same way. The one caveat I should mention is what I said about tidal forces. So the way that you can distinguish between these two things is if you have a very, very large box. So say, imagine this box is very wide, say an appreciable fraction of the width of the Earth, then Newton, in this case, could tell that it was not an uniform accelerating frame, because Einstein in his box, if he's just accelerating upwards, the acceleration will be the same throughout the box, whereas for Newton, the acceleration is actually towards the middle of the Earth, so depending on where you are, you'll have a different direction. It'll point right on the left and the right, it'll point in different directions, and so we can tell the difference that way. Similarly, if you have a very tall box, we know that gravity, of course, gets weaker as you get farther, so if you have a tall enough box, then Newton could notice that, oh, the acceleration is actually stronger at the bottom of the box and weaker at the top of the box, so you could tell that way. So if you have large areas of space, you can tell the difference, but Einstein's equivalence principle says just that locally, in sufficiently small areas, these two situations are equivalent. And that will be very important later on. So I'm going to start by introducing this equation. We're not going to get into it too much, but I just want to kind of put it up there to talk about it a little bit. This is Einstein's field equations. It's plural equations because these indices roll over a bunch of different, each indice rolls over 4 different values for the 4 dimensions in space-time. And what this quantity says is that this left-hand side quantifies the curvature of space. It quantifies how much space and time are curved. This right-hand side has 8 pi times the same gravitational constant as Newton times T mu nu, which is the stress energy tensor, and that quantifies how much mass and energy is in space. So the central result of Einstein can, I think, arguably said to be contained in this, in a sense at least, which is that mass curves space and time according to this equation. And so this sort of metaphorical picture that's used a lot is, so here on the left, if we have no mass, we have flat space, whereas if we put a large mass here, it'll bend space and time around it, leading to these curved elliptical orbits. So this is another example of that same argument. So if you have a rubber membrane and you roll a marble across it, and you have a TV camera up on top, and look at what happens, of course, you'll see the marble rolls in a straight line across. On the other hand, if you put, say, a bowling ball in the middle of this membrane and roll the marble and have your TV camera, you're going to see from the top, you're going to see it appears to take a curved path. And it's, of course, taking a geodesic curve, which is appears to be a bent curve, but the point is that within the curved space of this membrane, it's in a sense, the closest thing it has to a straight line, given that it's moving in a fundamentally curved space. Now, some of you, if you think about it a little bit harder, you might, you might be a little suspicious about some of this stuff. Of course, if anyone's more familiar with GR, then you'd also know this, that there's a problem with this metaphor, right? So if you take these two situations, the second one, I'm trying to make the argument that when you have curved space, then straight lines become curved lines. But of course, this situation you can describe completely fine with strictly Newtonian gravity, right? This is actually a curved surface in 3D space. You have gravity pulling it down. That means when the ball's on an incline, you'll have a normal force that pushes back on it. You can derive the acceleration of the ball, and it'll have this curved surface, curved pathway. So why do we even need to introduce general relativity to begin with? And the point is that this is a very limited metaphor. This is a useful way to kind of get your head around what we're talking about as far as curved space-time. But it's not the same thing. It's a metaphor that has a limited applicability, but it's certainly incomplete. So, before we get straight to GR, I want to have a little detour to discuss curvature. In particular, I want to talk about 2 types of curvature. First is what's called extrinsic curvature, and that's what we've been illustrating in these figures so far. So extrinsic curvature is the curvature that you get when you take, say, a flat 2-dimensional surface, and you bend it into a 3rd dimension. So say here you bend it around the surface of a sphere. So now you have a curved 2-dimensional surface that is the surface of the sphere. And so the curvature of this surface, the spherical surface, arises by extending a 2D surface into a 3rd higher dimension. And in this case, it's illustrated for a 2D curved surface, but you could generalize this to larger dimensions also. And that's, so in this case, if you have an XY plane, you bend it into the Z direction to obtain a curvature. So it's extrinsic in that the curvature is obtained extrinsically to the dimensions of the surface. You have to introduce an extra dimension to obtain the curvature. That's contrasted with intrinsic curvature, which is less intuitive and harder to visualize, but it's the curvature that's involved in GR. So I want to spend a little bit of time trying to explain what this difference is and how it works. This is an example. This little bug on a plate is an example that I got from Feynman, and I think it's a nice one. So the idea goes as follows. You have a bug on a hot plate of sorts, and the hot plate has a variable temperature that increases as you go out from the middle of the hot plate. And this bug lives in an alternate universe where there's a very large coefficient of thermal expansion, and there's also a very fast coefficient of thermal equilibrium. And what that means is that the bug, as he moves out farther from the center of the plate, he gets longer. His length and size extends. Any sticks or rulers or anything he brings with him will also extend as he goes out farther. And as he moves in, then it shrinks again. And the point is, if you have this bug on this kind of weird contrived hot plate, and you ask him to try to draw a straight line, you're going to see that he does this. And how do we know he'll do that? Well, so first of all, what is a straight line? The straight line, the easiest way to define it is it's the shortest distance between 2 points. And if he were to draw what appears to us on the outside to be a straight line, we'll see that's actually longer than the line that he drew here for him, because his ruler, as he goes towards the middle, is going to shrink, and he'll have to do more rulers end to end to draw that line. Whereas if he has this sort of arc bend out that goes out a little bit, then he'll have the right balance between keeping his rulers long and not making his pathway too long, looking at it from the outside, so that this is the shortest distance between points A and B. And the interesting thing about this is that these are these are different types of curvature, extrinsic versus intrinsic, but with the proper selection of the temperature gradient and the proper choice of the expansion coefficients, you can actually make this curvature identical to the curvature of a half of a sphere. So these, and not identical in the sense that they look the same, but identical in the sense that any straight lines that they draw will behave the same way, and the geometric properties of the spaces have the same degree of curvature. This is still, I want to point out, this is still only curving space into space. We haven't introduced time yet. To get the full GR description, we have to actually curve and bend space and time into each other. That gets even more confusing, but we'll get to that in a little bit.
I was looking at
Baby steps.
Question. That is still the shortest line you can draw between those 2 points, is that correct?
That's the shortest line you can draw between
Right,
the points. Yeah.
okay, and is it,
And that's how you would define a straight line as the shortest
so
line.
it's a straight line for,
That's a straight line in quotes, right? It's similar to the geodesic on the sphere.
It's a straight line for the ant.
It's a straight line for the ant,
Okay.
right? Because also for the
Right.
ant, photons also will do the same thing. So if he tries to look, that looks like a straight line to him also.
if you tried to measure it with some measurement, it's gonna be a straight line?
Right, it appears to be straight to
Yeah.
the ant,
Just trying
right?
to stick with them, and lays down the
Yeah,
stick.
gotcha, okay.
Right,
It's
yeah.
a straight.
All right.
Yeah, but you know, it's harder to visualize, right? Because it doesn't look curved, but the internal properties of it are curved. So I want to give you a few more examples. And so the thing, I guess the motivation here is that extrinsic curvature you can see, you can wrap your head around, that's a sphere, that's curved, and it's a little more intuitive. With intrinsic curvature, you can't visualize it as directly, so in order to quantify curvature for intrinsically curved surfaces, we have to go about it in an indirect, roundabout kind of way. So let me give you a few examples. One was the line that we had before. Another one is a triangle. So we know that the sum of the angles of a triangle in flat space is 180 degrees. If you draw a triangle on a sphere, and you define a triangle as 3 straight lines that connect, then you see that the sum of the angles is greater than 180. In particular, if you draw a large triangle that's an eighth of a sphere surface, then you'll have 3 90-degree angles. You can convince yourself of this, and that'll add up to 270, which is quite a bit larger than 180. And then I didn't have a figure to draw this, but you can, just looking at this, you can see if you did the same thing for the ant and drew a triangle, also each of those angles is going to sum to larger than 180 degrees, because it's a sort of bowed out triangle from our perspective. Excuse me.
Not less than?
No, some of the internal angles, because so if going from here, you'd have another bowed out line that kind of bends out this way, so that each of the angles will be bowed out, leading to larger internal angles for each of the 3 angles.
Hyperbolic. All right.
One other side note on this figure I just want to mention before we proceed is if you draw a really small triangle on the surface of a sphere, so we're all sitting on the surface of a sphere, if you draw a very small triangle, say at the beach, that presumably it won't have a whole lot of deviation from 180 degrees, right? So locally, the Earth doesn't appear to be very curved. It's only when you draw a triangle that's an appreciable fraction of the size of the Earth that you get a noticeable deviation in the sum of the angles. And that's going to become important later because curvature in general, if you zoom in really, really close to something, you don't see much curvature because they're generally smooth surfaces, except at singularities, which are more, maybe more of a mathematical artifact, like in the middle of a black hole, say. But in general, like you have to have an appreciable area before the curvature becomes measurable.
And what is that appreciable area? What scale are we dealing with on the Earth?
Well, for the Earth, it would be the size of the Earth, right? So an appreciable fraction of the radius of the Earth.
Okay.
Well, there was a Swiss fellow in the 18th century, so 250 years ago, who got this idea, climbed 3 different mountain peaks, which were visible from each other, set up a telescope with the ability to measure angles to each peak, and totaled up the angles, got 180 degrees to the best of his precision, but he had already figured out that that wasn't necessarily what he would get. He actually experimentally tried to measure.
Oh, interesting. When was that?
1789 is sticks in my mind, but
Yeah, it's not too long after Newton. That's interesting. I guess this is still more traditional curvature.
I might be wrong about the
That
date.
wouldn't work because, I mean, the light would still, would still follow straight lines. If it doesn't,
Yeah.
the light doesn't follow the curve, or, well, refraction, I guess, maybe, but anyway.
Interesting.
Well, it was an idea.
Yeah, it was an idea.
Yeah, I guess it
Until
didn't
you
work,
run the
but-
experiment, you can't really say.
One more example of the same type of idea is a square. So if you define a square as walking in a straight line for a certain distance, turning 90 degrees, walking that distance again, turning 90 degrees, and doing that 4 times. For flat space, of course, you'll come back to where you started from. But if you try to do this on a sphere, you'll see that you won't. If you try to do it on the bug's hot plate, you'll see a very similar result. So again, not to belabor this point, but what I'm trying to say is that, I'm trying to get through is that for an intrinsically curved surface, you have to use these sort of indirect methods to determine if it's curved, and that's how you measure and quantify the curvature. Right, so because intrinsic curvature is harder to directly visualize, we characterize it indirectly through deviations of the geometry from what we expect in flat Euclidean space. One further example that is important for our further developments is called parallel transport. So parallel transport is the idea that you have a vector, say here at point P, and parallel transporting it means that you move it along some path while keeping the vector pointing in the same direction as you move. So for flat space, if you parallel transport a vector around a closed loop, say I have a vector like this and I move it around in a loop and I bring it back to where it started from, the vector of course doesn't change at all. It points in the same direction when you return to your starting point. That is not the case for a curved surface. If you imagine having an arrow here at the equator and you parallel transport it straight up to the North Pole, it's going to point out that way. On the other hand, if you parallel transport it along the equator and then put it up towards the North Pole, it's going to point out that way. And this isn't drawn here, but you can imagine if you can complete the loop and then bring this arrow here back down to where it started, it'll point out this way, which is different from where it started. And parallel transport is really important because the amount that the vector changes after completing its loop is proportional to the amount of curvature enclosed by that loop. So it's a really useful way to quantify curvature because they're directly proportional. So you can do a little parallel transport in a loop, and you can see how much the vector changes, and that'll be related to how much curvature is enclosed by that loop. Okay, how does this all relate to Einstein's equivalence principle, right? So we talked about a bug on a hot plate, and he may draw curved lines, but he's not flying through an elliptical orbit when he thinks he's just standing there, right? Remember, the equivalence principle was trying to point out how an accelerating frame in space is the same as not moving and being in a gravitational field. Those are actually the same thing in some weird way. And the reason that the bug doesn't exhibit that property is because the hot plate that we're talking about was strictly bending space into space. And in GR, you also bend space and time into each other. It's not just between the spatial dimensions. And that opens a whole other bag of worms. Can of worms, I guess you don't have bags of worms. Which we're going to try to explain a little bit, but it gets a little more confusing here on in, so prepare yourselves. Okay, so that leads us to time and space as space-time. You guys may have seen one of these diagrams where we have just one spatial dimension on the x-axis and time on the y-axis, and then they draw these light cones. So this is getting, of course, back to special relativity, Einstein's earlier theory. And he showed that there is a maximum speed limit of any particles or anything in the universe, which is the speed of light. So nothing, no information, no particles, nothing can travel faster than the speed of light, which means that if you have a particle here, it's hanging out at this point in time and space, it cannot be causally influenced by anything that's out of this cone, because anything that was in its past that influenced where it is now or what it's doing would have to be inside this cone, because something over here wouldn't be able to get there in time to influence it in any way. And of course, light itself travels along the perimeter of this cone. And so the fact that the speed of light is constant is what connects space and time together. It's sort of what sews them together, because there's this absolute relationship between the two. And so, for example, as you guys probably know, when you move faster, time slows down. And as you approach the speed of light, time actually stops. Which, if you think about what it means, what it would be like to travel along with a photon on as light travels, you can't really do that because we have mass, so we can't travel that fast. But you can still do it as a thought experiment. If you were to move at the speed of light, time would stop at that point, which means that when a photon, say a photon's emitted from a distant galaxy and it comes through space and then hits your eyeball, that photon, from its perspective, was emitted at the same time that it's absorbed by your eye. It doesn't experience the passage of time. And so there's kind of a trade-off in this sense. And this bullet here, the physicists in the audience will probably roll their eyes and or object to this, but I think it's a useful way to think about it, if it's an imperfect analogy. I like to think of it as you have a limited amount of motion in 4D space-time, and you can allocate that motion through either the space or the time direction. So if you're just sitting here not moving, you're moving through time at a certain rate. As you change to be moving faster through space, then that motion decreases through time and it's directed more through space, if that makes any sense.
Well, you should point out that it's all relative. Because
Certainly, it's all relative.
If you're sitting on a rocket that's going 99.999% the speed of light, and your rocket doesn't have any windows on it, it feels like being in this room. As far as you're concerned, your watch is running
Right,
normally.
certainly, yeah,
and
there's no absolute position, so it's all, it's all based on
Well,
the
if you
reference
pull out
frame.
your flashlight and try to measure the speed of light, well, it's
Certainly, right.
microwaves is actually how we did it in school. But you try
Yes,
to measure, you still get the speed of light. Everything looks perfectly normal to you, no matter how fast your rocket ship may be going.
Right, yes. I guess to get this trade-off, you
So-
really have to have two observers, so you can have one observing, the other one moving, because if you're just by yourself moving,
'Cause it's
you
just
can't really
relative otherwise,
notice anything.
right?
Right, sure. Fair point. In any case, so space and time are sewn together into this more coherent space-time, but in one way you can look at it because the more you move through space, the less you move through time, so they have this interrelation, and they're tied together through the speed of light, which is a fixed constant. So that's kind of how they rope together into this more coherent structure of space-time. So to generalize our notion of intrinsic curvature to space-time, that results in a freely falling object being at rest in the curved space-time. So the way to get from the bug on the hot plate where things are bent maybe, but you're not mixing accelerating frames and stationary frames. But once you start mixing space and time together in this way, in a specific way, which I'll explain a little bit more in a little bit, and realize this is still not really well motivated, but by mixing space and time together, you can get this kind of weird situation where something that appears to be accelerating to one reference frame, to one person, from that other person's perspective, they may feel like they're not moving at all in this other reference frame because space and time are mixed in a complicated manner. Okay, before we get to GR, I have to do a very brief mathematical interlude. I apologize. But I just wanted to explain some notation. We're not going to get into this too much detail, but I wanted to explain this concept called a mathematical concept called a tensor. So there's two versions of this that most of y'all are probably familiar with, which are scalars and vectors, which are respectively a rank 0 tensor and a rank 1 tensor. But this concept generalizes a more complicated thing. So a scalar is just a number like a mass or a charge or whatever. A rank 1 tensor, which is a vector, is a quantity that has components. So a three-dimensional vector has, it's an arrow that points in some direction, say it's velocity. In general, in GR, you deal with 4 vectors. So this notation v mu means that mu takes 4 values, typically denoted as 0, 1, 2, 3. So 0 is time, 1, 2, 3 are the 3 spatial dimensions. And what exactly the time component of velocity means, I'm not going to get into, but you generalize the notion of a velocity to include 4 dimensions, so it's a 4-dimensional vector. But you can keep going. So you can also have a rank 2 tensor, which is a matrix. So for 4D space-time, that would be a 4x4 matrix. So you have 16 numbers in a particular reference frame to denote the 16 components, because each of mu and nu will go through these 4 different values for the 4 dimensions. And then maybe to motivate this a little bit, like, well, what's an example of that, just so you can kind of conceptualize it. You could take the example of if you have your bathtub and you drain it, and say you wanted to have an equation to describe what is the velocity of the water in your bathtub at each point in the bathtub. And to do that, you could use a matrix, a rank 2 tensor. And you could do that as follows. So this first index mu, and for the bathtub example, this is just going to be a 3-dimensional one. We won't bring time into it. But so you have mu could be 1, 2, or 3 for say x, y, or z. And the first index would describe what point in the bathtub you're talking about. The second index would describe what is the velocity of the water at that point, which is also a vector. So you need 2 indices because there's 2 quantities you're trying to describe in a single thing, right? So you have this matrix to describe what is the velocity field of the water in your bathtub as it's draining. And there's a different direction of the water velocity at all these different points. So you need 1 index to describe that. And you have the other index to describe what point you're talking about, where you're trying to say what the velocity is. And this keeps going. So we have this Christoffel symbol, which we'll get to in a little bit, which is then a rank 3 tensor, which you can look at as a 4x4x4 cube through a 3-dimensional matrix where you have 4 components along each of the 3 dimensions. And then you generalize this so on and so forth, where you have higher rank tensors. Don't fret too much of that's a little confusing. I just wanted to briefly introduce the notation because we're gonna delve into the hairy stuff. Okay, Riemann curvature tensor. You guys ready? So this is the expression for the Riemann curvature tensor, and if you recall, this R may remind you of this Einstein equation that we showed you on the earlier slide. And these aren't the exact same quantities. These R's are actually, they come about, this is the Ricci tensor and the Ricci scalar. They come about from averaging this quantity in some sense over some of its indices. But this thing, what this means is it quantifies the curvature of spacetime in a very concrete way. And you arrive at it by transporting a vector in an infinitesimally small loop. So if you take this, like we were talking before, when you transport a vector around the loop, that will give you some measure of the curvature inside that loop. And so if you do it for an infinitesimal volume, of course you'll only get an infinitesimal amount of curvature because things aren't very curved over small areas. But you can still quantify what that infinitesimal curvature is, and it's related to this Riemann curvature tensor. So what on earth does this expression mean? We have now a rank 4 tensor. You can see why this isn't ambitious to explain this to a lay audience without really getting into the weeds, because this stuff is pretty complicated math, right? How do you visualize a rank 4 tensor? But I'm going to try, so we'll see how this goes. So we have two main things going on in this equation. We have these gamma functions, which are 3 tensors, which are called the Christoffel symbols. Then we have some derivatives of them, or combinations of 2 of them that occur in the terms. So let me try to motivate what the Christoffel symbols are. I'm going to use this diagram that I shamelessly stole from Linus's talk. So thank you, Linus. So this diagram is showing some things we haven't talked about. TP is the tangent space, which he'll explain more later. E1 and E2 are basis vectors, and M is our manifold, just the structure of space that we're dealing with. And so one of the tricky things about GR and about curved spacetime is that your basis vectors, so a basis vector is just an normal Cartesian space. You have X, Y, and Z, or your 3 directions that you're dealing with. And one of the confusing things about curved space is that when you move to different points, your basis vectors themselves move to point in different directions. So if you're looking at extrinsically curved surfaces, right, you can always step back and say, okay, yeah, the surface looks curved, but I have this global coordinate system that's going to stay the same to let me kind of wrap my head around what's going on. That's not the case for intrinsically curved surfaces, because the basis vectors that describe the dimensions and directions of the space themselves actually morph and change as you move to different points. And in particular, one thing you could think about in terms of these basis vectors is you could consider, say we have this E1 basis vector, which we can call X. So that's the X basis vector. If you move this basis vector to a point along, say, the Y direction, you could ask, how much does that basis vector change into the Z direction? That would be a reasonable question you could ask. And that turns out to be the Christoffel symbol, gamma X, Y, Z. So, and then this is, of course, a rank 3 tensor, so there's actually 64 different values of all the different combinations, but those are all the things that are relevant to the curvature of the space. You have to ask, how does this basis vector change in each of the 3 different directions when that basis vector is moved in each of the 3 different directions? And so that leads to this quantity here. So putting all these things together gets you the curvature. Why, on this one, acts as an extra 4th index here. Why does that thing get introduced? And the reason for that is because to quantify curvature, you have to transport a vector around a small loop, which means you don't just need to know how you don't just need to know how the basis vector changes. You have to know how the change in the basis vector changes as you go around in a loop, which is why you have this partial derivative here to quantify that change. And there's also these terms involving combinations of Christoffel symbols, which I'm not going to motivate in too much detail. But very broadly speaking, that's what this expression is saying. It's quantifying how the geometry changes as you go around in a loop when your whole business is much more complicated because you have to bootstrap your changing. The thing you're using to measure the space is changing as you go around, which makes the whole problem a lot more complicated, which is why you have to deal with these ridiculous looking equations. How you guys doing? You all right? Okay, I want to introduce another quantity that's relevant for this, which is the space-time interval. Before I get into that, I want to talk about the simpler version in simple Euclidean space, which is the invariant distance. As a lot of you probably know, if you have just normal flat Euclidean space, and you have 2 points in that space, you can calculate the distance between those 2 points using the Pythagorean theorem. Right? If you take the square of the distance in this direction plus the square of the distance in this direction, that equals the square of the actual distance between the 2 points. And an important part of Euclidean geometry is that if you rotate your reference frames, or you move the origin around, or you do whatever you want to it, and you remeasure this value delta s, sorry, this should be delta s over here, not s. If you remeasure it in some other reference frame, like this tilted one, y prime and x prime, you'll find that delta x prime is different from delta x in general, and delta y prime, the distance between these two things along this direction, is also different from delta y. However, the overall distance between the 2 points, so the sum of the square of each of those two will be the same. So delta s squared is the same in each of these cases, even though the individual parts that lead into it are not different. So the Pythagorean distance s is unchanged when you change coordinate systems. That extends into general relativity, and also this is actually a special relativity result, but it's a little bit different, and we have now the invariance of what's called the space-time interval. So you have a similar quantity, and indeed the spatial component of this is the same. Delta x squared plus delta y squared plus delta z squared is just the Pythagorean distance. But space and time are combed in together, and space, you will notice, time has this minus sign in front of it plus a factor of c, which changes the behavior a little bit, and it has some interesting properties. This minus sign, I spent a long time thinking about it. I think I kind of understand it at least a little bit. It's partly related to why you have this trade-off between movement and time and movement in space that I was talking about before. Because there's kind of a trade-off in an interval. If you have some interval, sorry, let me back up a second. So an interval now is a little bit different. This delta s squared is now delta s squared between 2 points in space-time. A point in space-time is a point in space at a particular point in time. So if you have a point in space at one time and another point in space at another time, then you can quantify that, you can calculate this value delta s squared, and that value will be the same regardless of how fast your reference frame is moving, where you are, what you're doing, it'll always be the same. But it's not the same in that all these quantities are added, the time has a minus sign in front of it. And so there's kind of this trade-off there, like if you go to a frame where there's more motion in space, that means that there will be less motion in time in that frame, because the overall sum of this has to be invariant. So if you, so maybe another way of saying that is if you shift to a frame that's moving real fast, so that say delta x squared becomes very large, to make this quantity not change, that means that there has to be a trade-off between the two things in that sense. There's a little hand wavy of an explanation. But so anyway, point being, when you change to a new reference frame, say with the primes on it, you will have the same calculation for delta s squared. One interesting thing about this is that when you do a transformation like this, t prime and x prime are no longer necessarily perpendicular. If you boost, you can actually get it where according to the unprimed reference frame, they see the new axes bent into each other a little bit. Of course, the difference between them will still give you the same speed of light because the speed of light is constant. There's a lot more I could say about this. I apologize if this is confusing. There's just so much to fit into 45 minutes. But I guess one thing I would mention is that there's an important element of light behaves in an important way in reference to this expression. In particular, light follows these paths where x equals c times t. Sorry, it's a little bit of mixed notation. Some of my expressions are general relativists. General relativists always set c equal to 1, so they drop the factors of c. And some of these was pulled from a different source where they include c. In any case, these lines where x equals ct actually would have the case that s equals 0. And no matter how you change your reference frame, that'll always be the case. Just wanted to make that as an aside because that'll be relevant later when we talk about black holes. Okay, this brings me to the metric. So if we have this expression for the interval between 2 points, which is shown here, you can also write that as a matrix, which is called n mu nu, where it's a diagonal matrix, and this is the case for flat space, and there's just a negative sign corresponding to the t term, and a positive 1 for these other 3 terms. And it's a diagonal matrix, and that's because all the terms in this interval contain only delta t or delta x or delta y. There's no cross terms. Although in general, for a general relativity case, if there's moving masses and different numbers of masses, you can have off-diagonal terms in this matrix, which is manifested on this side as having mixed terms, delta x, delta t, for example, or delta x, delta y, and that type of thing. And my reason for going through all that was just to get a little bit of motivation and explanation of what this equation even means. This is the Schwarzschild metric, and this is a solution to the geometry of space and time for the specific case where you're outside of a spherically symmetric body. So say the sun. You're outside of the sun, and you want to quantify how does this interval behave if you have 2 points in space and time. How does the interval behave? It doesn't behave the same way as it would in flat space because there's a mass there in your vicinity, it will distort space and time in this specific way. So it changes the behavior of these two parts of this interval. And I have drawn here what these two terms look like. And a few things about this. So sorry, precursor. So this is in spherical coordinates. So r here is the distance from the center of your object. And d omega squared is the solid angle element, which since it's spherically symmetric, you can kind of just put that off to the side because it doesn't affect very much. And if you look at this, you see that there's some strange behavior of this whole expression at 2 points. One is at r equals 0, because if r goes to 0, this thing goes to infinity, and this thing goes to 1. I'm sorry, not goes to 1, it goes to this goes to 0, excuse me. So this behaves oddly at r equals 0, and that's at the middle of this, what we're calling an infinitely dense point mass. So that's weird. That's a physical singularity. There's also weird behavior when r equals 2gm. Again, I apologize for the mixed notation. This expression is setting c equal to 1, so it's actually 2gm over c squared. And that value turns out to be the Schwarzschild radius of a black hole. You guys probably have heard of this. That's the event horizon where there's no escape when you get closer to it. And you can see that there's weird behavior there, right? So when you get to that r equals 2gm, for the r squared term, it goes to infinity, whereas for the term related to the time, it goes to 0. So odd behavior there, and what exactly is going on? A couple things are going on. But first of all, let me give a little bit of physical context. So for most spherical masses, planets and stars, this point where r equals 2gm over c squared, that occurs way inside of the object. So for the Earth, the Schwarzschild radius is 9 millimeters. And when you're inside the object, this equation no longer holds. So this expression was derived assuming that you're outside of a spherically symmetric mass. Once you get inside the interior, then you have to do a different calculation. You're basically assuming that all the mass is inside of whatever point you're at. So, point being that for the Earth and the Sun, since they're much, much larger than these sizes, there is no black hole and there's no event horizon, because by the time you get to where it's 9 millimeters from the center of the Earth, you're no longer outside of the Earth, obviously. But what it does mean is that if you're able to mash the Earth down to be 9 millimeters wide, if you had a really big vice grip and smashed it, it could turn into a black hole, but it would be a little difficult to do. And similar for the Sun. Of course, the Sun is much bigger than 1.9 miles. So that's one way to get a black hole, is you can smash something down to where it's the size of the Schwarzschild radius. The other way to do it is to keep adding mass onto the object. So for the Sun, if the Sun was about 20 times its mass, if you had 20 of our suns and mashed them together, then after it completed its solar cycles, it would collapse down under its own weight, causing it to become dense enough to where all the mass is contained within the Schwarzschild radius, and it would turn into a black hole. So, of course, in that case, if it was 20 times the mass, it would have to be 38 miles would be the Schwarzschild radius, because it would be 20 times larger than this. A little bit more about the event horizon. And I know I keep apologizing. I guess I'd like to recognize that, depending on how much background you guys have in this, you probably don't really understand where this came from. I didn't derive it. I'm just kind of talking about it, which is the limitations of the medium, I suppose, and the depth of the lecture. But my goal here is just to kind of just sort of talk about what some of the terms in it do, what it looks like, just give you a little bit of a sense. And I realize a lot of this won't make full sense. Maybe we can address some of these questions in the Q&A. In any case, so, but the big picture here is that this interval ds squared quantifies in some way the geometry of space around an object, and it has this weird behavior once r gets smaller than this number. And it turns out that what happens when r gets smaller than this number is time and space bend so much around themselves that the direction of outside of the black hole no longer exists. So if you have, for example, say you're in a spaceship and you get sucked inside the event horizon and you try to escape, you'll actually, so by trying to escape, I mean you accelerate, so you have, say, some rocket boosters that aren't crushed by tidal forces, and you try to escape, you'll actually hit the middle of the black hole faster because you're trying to escape, because space is so bent that the direction of outside of the black hole no longer exists. Space is just totally contorted around itself so that every direction points in towards the center, which is kind of an interesting result, I thought. Okay, final slide to conclude this. I just wanted to talk about one other cool thing about black holes. And the question is here, what happens when you shoot light into a black hole? So we can figure this out by remembering what I said earlier about how for light, this interval ds squared goes to 0. And we're going to imagine shooting the photon directly into the black hole along the radial direction, which means that this d omega squared will go to 0. In that case, we have this equation here, which we can just solve for dt dr. So dt dr, remember, is the slope of the light cone in the tr plane. And then this quantity, this whole quantity here, 1 minus 2gm over r to the minus 1, is graphed here. And you see that as r approaches 2gm, it goes to infinity. This term gets very large, which means that the slope of the light cone gets very, very large. Which means that as you shoot a photon to the black hole, and from your perspective, sitting back watching the light get to the black hole, its light cone starts to close up as it approaches the event horizon. And it'll actually take an infinite amount of time before you see the light get to the event horizon. And that seems crazy. That means that light never gets inside a black hole. It does, it gets sucked in from its perspective. And this is where it gets kind of into an interesting instructive point about relativity, that from your perspective, sitting back here, from your frame of reference, as the photon gets to the black hole, it does slow down. It takes an infinite amount of time for it to ever get to the event horizon. However, through some complicated manipulations using different coordinate systems, if you change your coordinate system to see, say, the one that's inside the event horizon to see what's happening, you'll see that from the perspective of the photon, it does actually get in. So it's just sort of an artifact of the, it's interesting because it points out how fundamentally different observers and different reference frames, how fundamentally different their perception of time can be. So from our universe here on Earth, it takes an infinite amount of time. For the universe of the photon that's traveling in, it has no problem smashing through the event horizon and hitting the middle. It's just kind of an interesting relativistic point, I think. So, with that, I would like to thank you all for your attention. These are my references where I stole a lot of these figures from. And thanks very much. Maybe, let me know if you have any questions.